Hey guys, welcome back. Just like I promised, I'm here with my first topic video. Today, we are slicing through data with one of the fastest sorting technique, QuickSort. QuickSort is a divide and conquer sorting algorithm that works by selecting a pivot and partitioning the array around it. First, we should select a pivot element. You can get first, last, middle or random element as a pivot. Then split the list up according to element greater than or less than pivot element. And next repeat the same process left and right subarrays recursively. So we have unsorted array. We choose the pivot element. In this case, we choose last element as the pivot. Step 2. Partition the array. In this array, all elements smaller than pivot go to the left side and all elements larger than the pivot go to the right side. At the end, pivot is in the correct sorted position. Now let's see how the process. So we have an unsorted array. Let's see how this sort in QuickSort. First, we should select a pivot element. I choose 4 as the pivot as last element of this array. Next, that pivot element compare with all other elements. First, to compare with 4, 2 is less than 4, so it stays left side. Then 5 compare with 4, 5 greater than 4 and 7 compare with 4, also 7 greater than 4, both will move to right side. Then 1 compare with 4, 1 less than 4, so move to left side, swap with 5. 9 2 greater than 4, so move to right side, then 4 swap with 7. Next, then apply this process right and left subarrays. Left subarray is 2 and 1. We get the pivot element as 1. So 1 compare with 2, 2 is greater than 1. So move to right side and 1 and 2 get 0 and 1 indexes on array. Then right subarray is 5, 9 and 7. 7 is pivot element. First compare with 5. 5 less than 7. So stay left side. 9 compare with 7. 9 greater than 7. So move right side. 7 get index 4. 5 get index 3 and 9 get index 5. After all that, we can see sorted array like this. Next, let's see how QuickSort code implementation. I have clean and simple QuickSort code in Python. I will explain it briefly. First, here is define a function QuickSort that accepts the array we want to sort. Next line, if the array has 0 or 1 element, if it is already sorted. That's our stopping condition. So, in that case, we just return the array as is. Otherwise, we proceed with QuickSort steps. Next line, we first use pivot element. In this code, I am using the middle element as the pivot. Next, then we divide the array into 3 parts. First, number smaller than the pivot, numbers equal to the pivot, numbers greater than the pivot. Next step is We then repeat the same process for smaller part and greater part. This is where recursion happens. The function calls itself. You can see. Finally, when all the parts are sorted, we join them together to get the final sorted array. So the idea is simple. Pick a pivot, split the list, sort all parts and combine them all. Then let's see why use QuickSort. It is very fast for large data sets, uses minimal extra memory, works well with computer cache systems, and it is the go-to algorithm in many programming libraries. Programming libraries, finding rankings, database systems, and scientific computing are there. We use QuickSort in real life. Let's talk about the time efficiency of the QuickSort algorithm and see how it is compares with other sorting methods. QuickSort is one of the most widely used and efficient sorting algorithm in computer science. It follows a divide and conquer approach, which means it divides the problem into smaller subproblems, solve them individually, and then combines the results. In QuickSort, we first select the pivot element of the array. The array is then partitioned into two parts, elements smaller than the pivot and elements greater than the pivot. The process is repeated recursively until the whole array is sorted. Now, when we analyze the time efficiency, QuickSort performs differently depending on how the pivot divides the data. In the best case, the pivot divides the array into two nearly equal halves each time. Because the data is split evenly, the algorithm needs to perform about log n levels of recursion, and each level processes all n elements. This gives a time completely of order n log n, which is very efficient. In average case, the pivot might not divide the array perfectly, but still reasonably well. Even then, the average time complexity remains order n log n. This is why QuickSort is considered one of the fastest sorting algorithm in practice. However, in the worst case, QuickSort can become inefficient. This happens when the pivot is always the smallest or the largest element. For example, when the array is already sorted and nearly sorted, and we always choose the first element as the pivot. In that situation, instead of dividing the array, the algorithm keeps creating very unbalanced partitions, leading to a time complexity of order n squared. But in real-world applications, this problem is often avoided by using a randomized pivot selection, which helps maintain a good performance. Another advantage of QuickSort is that it's an in-place sorting algorithm, meaning it does not need the extra memory to store temporary arrays. It only uses about order log n space for recursive calls. This makes it more memory efficient than other divide and conquer algorithms like merge sort. Now let's compare QuickSort with other popular sorting algorithms. First, merge sort, like QuickSort. Merge sort also follows the divide and conquer principle. The main difference is that merge sort divides the array into equal halves every time, sorts each half and then merges them together. This guarantees a time complexity of order n log n in the best, average and worst cases. However, merge sort requires order n extra space for the merging processes, so it's not as memory efficient as QuickSort. Merge sort is also a stable algorithm, meaning that if two elements are equal, their relative order stays the same. Because of this, merge sort is preferred when stability is important, for example in sorting records or strings. Next, we have insertion sort. Insertion sort works by taking a one element at a time and placing it in its correct position in the sorted part of the array. It's very simple and performs extremely well when the data is small or almost sorted. Its best case time complexity in order n. But for larger or unsorted data, the average and worst cases are order n squared, although it's lower for big data sets. Insertion sort is often used inside hybrid algorithms like sort because of its efficiency on small data segments. Moving to selection sort, it repeatedly selects the smallest element from the unsorted portion and places in the correct position. It's easy to understand but not very efficient, since it always takes order n squared time regardless of how sorted the data is. It also does not maintain the stability of equal elements. Finally, we have bubble sort, one of the simplest sorting algorithms taught to beginners. It works by repeatedly comparing and swapping adjacent elements. It works by repeatedly comparing and swapping adjacent elements if they are in the wrong order. But bubble sort has a best case of order n when the array is already sorted. But in the average and worst cases, it performs order n squared swaps, which makes it the slowest of all. It is mainly used for teaching purposes rather than real applications. So, when we look at all these algorithms together, we can say that QuickSort provides the best balance between time and space efficiency. It sorts faster than merge sort in the most cases and uses less memory. Although merge sort is more consistent, QuickSort's average case performance and low space usage make it the preferred choice in many programming languages and libraries such as Java, C, and Python. As the summary, QuickSort is the most efficient general-purpose sorting algorithm with the best and average time complexity of order n log n and manageable space requirements of order log n. It's the go-to choice when you need high performance and memory efficiency. I think you all have some idea on QuickSort now. So I will come with new videos soon. Until then, stay tuned with me. Thank you for watching. All. Bye.